Hey everybody. Do you know what this song is from? Hey, good morning D Stratus. Good morning Mike. Good morning Pika. Close. Evaluated 0. Close. Different gaming engine. Good morning Kipros. Good morning Pika. Hey there Kate. Good morning. Good afternoon, Shrek. No printout. There's no printout today. You have this cup? You're literally drinking out of it right now. I'm having a little smoothie. Good morning, Benny. Liam says, do you think we could push off the last problem by another 6 days? So I could put MAE 444 homework 4 question 4 do 4 on my paper. I appreciate the ideal that you were grasping for and the artistic vision of that request. But we won't do that. You have a Target knockoff of this? You don't have the authentic? I don't know where we got. I mean, we obviously got it at Starbucks, but I think it belongs to Hannah. What smoothie is it? It's like it has some it's green in color. You can't really. You can see residue on the straw. Wait. I think it has spinach, some berries, some orange juice. Ooh, 4/4 is Antonio's birthday. Happy early birthday, Antonio. Exciting. Wait, nobody knows what this song is from? This is from Final Fantasy VIII. Hello, that guy who stings. Hello, Nookus. Hello, Belkit. Okay, we're gonna switch over. All right, guys, are you ready to do a code along today? Hello, Amin. Okay. Get MATLAB ready. You are not going to want to miss out on this fantastic code along that we're about to do. Good afternoon, Quaron. Good to see you. Okay, I'm gonna come over here. Gotta change this date really quick. I don't want to look at MATLAB after this past weekend. I understand. Okay. Root, locus, technique. MAE 552 is too much MATLAB. Which one is 552? Okay. Heuristic optimization. That's taught by Shomo Chowdhury? Is that right? Okay, gotcha. He's a good guy. I've never understood what the heck heuristics means. I thought heuristic was kind of like ad hoc, and that's another word that I don't know entirely what it means. But that it's like unique to each problem, I thought. Somebody in the class would know way better than I do. From what I understand, it's just like stuff you made up. Yeah, I thought it was something like that, like genetic algorithms. It's like, well, we're gonna optimize this like genes mutate. We're gonna try to imitate the evolutionary process, and it's like, wait, why are we doing that? Oh, just let's try it. See what happens. Okay, get MATLAB open. Ad hoc means as necessary or as needed. Okay, thank you. I'm going to remember that. Okay. So what we're going to... Oh, this thing isn't plugged in. Yeah, that's better. We'll code in this class ad hoc. Technique, Squidward. All right. So we're gonna use the same plant that we've been using the last couple days. It's like define alpha as 1 or 0.5 depending on the problem. Me? Why? Yeah, I don't know. Yeah, good illustration. So this is our plant. The plant is the system that you're trying to control. All right, and so we're putting it in a feedback loop. Our controller is D, and then we're just doing a simple feedback structure like this. Plus, minus. That's our reference, and here's our output. And the closed loop poles that we're going for, these are in the discrete plane. And we're designing a controller that's going to place our closed loop poles right here. What should I name this script as? Let's do that right now. Because I have to save mine. Root locus technique automation. That could do it. Let's do it. Root locus, automation, and I'm even going to put the date. You could call it Donk Monday. That's a winner. That's a winner. Estes code 2. All right, we have an Estes code 1. Now we're going to have an Estes code 2. Okay, so you've named this. Wait, let's go back. So you've named it. Now, what we've discovered... Well, okay. We already know that our controller is going to look something like this. It's going to have a gain. It's going to have 1, 0, and 1 pole. So we're going into this code knowing that I want a controller that looks like this. Twitch just now told you that I went live. Well, it's a little behind the ball on this one. All right. So we're going to jump back in between these notes and the code. Let's go over to the code right now. We're going to do some bookkeeping at the beginning. We're going to set up our sampling frequency. Can any of you type as fast as I just typed right there? I learned that from RuneScape. All of my typing speed came from that. Okay, here's our sampling period. It's 1 divided by the sampling frequency. So this is in seconds. Let's put our transfer function. This is our transfer function G. That guy who stinks can do it. We need to have a typing speed competition. Don't they have some games online that we can use? All right, we're going to put in our plant. So there's 3 arguments. There is the numerator of your transfer function, the denominator, followed by the sampling period for a discrete time transfer function. So we just wrote what our plant is. It was 0.0158 times z plus 0.876. I was literally doing that yesterday with friends. I think it's typeracer.com or something. Can we compete? Okay, we might have to try that after class. We need to put it to the test. All right, for the denominator, we're going to do it this way. We're going to make the polynomial that has a root at 1 and a root at 0.6703. Give me a day to practice? No. No. Okay, this is our plant transfer function. And let's also put in our desired closed loop poles, Z star. And I'm just going to put the positive conjugate for now. So don't forget the, let's see. So these are desired closed loop poles. Z star. Okay, now let's go back to the notes really quick. Because to achieve these desired closed loop poles, this is what the root locus method is all about. We have 2 criteria. The first one is the angle criterion, which is the angle of, you guys have to be sick of me writing this at this point, but it has to be drilled into your memory banks. That angle has to be pi. And this means you can break it up like this. Angle of G plus angle of D equals pi. I might need the times I. Actually, you don't. You don't need that. And I'm not even joking. Okay, so this is the angle contribution that we need from D. It's going to be pi minus the angle contribution of G of Z. Yeah, today I'm just saying no to everything. So that's the theme of the day. You've been wasting a lot of time. Think of how many asterisks you could have saved and how many carpal tunnels you could have prevented. But now you're going to have to endure. So we're going to do this part in MATLAB right here. We need this. We need to automate this angle calculation right here. All right. So first we need the angle contribution of G. Okay, so here we are using the angle criterion. So I want to get the angle of G first, evaluated at Z star. And so we have this eval function. So we're going to evaluate G at Z star. And then there's this convenient angle command. And then the angle that our controller needs to make is pi minus the angle of G. So this is angle of plant evaluated at z star. And this is the necessary angle of controller D. If we want our closed loop poles at z star, then this has to be the angle contribution of D. All right, now let's go back over here really quick, because the angle of D at z star, we can break it up. So I'm looking at this transfer function up here. It's the angle of K, which is just 0. That's why I often leave it out. Plus angle of Z minus Z1 plus angle of Z minus P1. So this is the angle of that overall function. You can break it into these pieces. Oh, and these have to be Z stars right here. So this is equal to the angle of Z star minus Z1. And this term, you can write it this way, minus angle Z star minus P1. So there's not one way to do this. We need the overall angle of D to be whatever we just calculated in MATLAB. And it's around 51 degrees. So there's an infinite number of combinations of these terms that you can pick so that the overall angle comes out to be that. And this is kind of why we're automating this in the first place. There's so many answers, you don't want to do this by hand. But there is so the way we're going to do this is first we're just going to pick randomly, well not randomly, we're going to pick an angle for the 0. And then based on that pick, we're going to figure out what the angle of the pole should be, and then we'll proceed from there. This angle here, it can't just be anything. And we talked about this a little bit last time. There's a minimum angle it can be, and there's a maximum. The maximum that it can be is 180 degrees. And the minimum that it can be is the angle of your controller evaluated at Z star. Like the overall angle, which is like, I think 51 degrees in this case. So the smallest it could be is 51, the largest it could be is 180. So I'm gonna define in MATLAB a bunch of combinations over that minimum to maximum range. Let's do it. Okay, so let's, oops. So we're making range of possible angles of 0. And I'm going to call this oh my goodness, angle of Z1. All right. But we have to decide how many controllers we want to look at. How many possible controllers we're going to make. And I'm going to call that number of controllers. Let's just start with 10. And we can do more, but let's just start with 10. And when I'm defining the angles of Z1, the way I want to do it, I want to use the linspace command, which can make a vector for you. Let's start with the min angle, the minimum possible angle for Z1. And we'll go to the max angle Z1. And the number that I want in this vector is 10, the number of controllers. So this linspace is going to pick 10 angles between this range for me, and we have to define these. So like I said, the minimum angle would be the angle D that we calculated up above here. And we're doing this in radians, so the max angle, which is 180 degrees, that's just pi. So we're going to go from here to here, and we're just going to pick 10 numbers. And you could easily change this to 100 or something, but we're starting with 10. Oh, another thing. often if you find where the 0 is that corresponds to these angles, like, okay, this for example, if I have the 0 making 180 degrees relative to Z star, that's actually going to put the 0 at positive infinity. And MATLAB is going to like throw an error eventually because it's it'll return like not a number or something. So what I like to do is I like to go not all the way up to the max angle. So many angles. So what I like to do is I like to go a little shy. Let's go like 10 degrees shy of the max angle. So 10 degrees is 10, but we got to convert this to radians. So we're not going to go all the way up to 180 degrees. We're going to go up to 170 degrees. Same thing with the minimum angle. Let's add a little padding on there. So I'm going to start 10 degrees above the minimum angle. So we're going to pick 10 angles kind of interior of those maximum limits. Okay. Good. Now, if we have the angles of the zeros, we can calculate the angles of the poles. I'm going to go back over here really quick. When I'm talking about the angle of the pole, I'm talking about this angle right here. I'm not to get confusing, but I'm not talking about this angle. You could do this different ways, but when I'm talking about the angle of the pole right now, I'm talking about this. So it's actually going to come out to be a positive angle, but I'm subtracting it, and so it's all going to work out. So if you look at this, the angle that I need for my poles, okay, so Z minus my pole, it's going to have to be the angle from the 0, which now we have like 10 options, minus the overall angle of the controller. So this is what I'm going to put on my next line of code. These are the corresponding angles of the zeros that I need. Let's do it. So it's going to be angle Z1, so there's like 10 of them, minus the angle of D. Heck, why don't we run the code at this point and just see if we've encountered any errors up till now. No errors. Okay, let's look at the angles of the zeros. And you know what? I'm going to convert it to degrees right now. I'm going to multiply it by 180 divided by pi. So it goes from, because this is times 100 here, so this goes from 61 degrees, which is 10 degrees above the minimum angle, which is like 51 degrees. And then we go all the way up to 170. So we went 10 degrees shy. Meerkat says, what's the last command after the comma in the linspace command? And Easy says there's also the built-in functions radian to degrees and degree to radians. Ooh, good to know. Wait, in the linspace? Oh. The number of controllers. Won't angle P1 equals 0 also return an error later? Yes, but look at what we did. We truncated the range of Z1, and then that truncated variable goes in here. So this angle of P1 is going to be based on that reduced range, and so we don't really have to worry about the limits here. Can you please go back to the poly part for a second? Right here? Around line 8. That's all of our codes so far. Got it, got it. Let's look at the angles of the poles really quick. So you see, we go, let's see, 17 degrees. Wait, oh no, this isn't multiplied. Oh, watch this. I'm going to use that command that Easy suggested. Radian 2 degree angle P1. Okay, so this is times 100. So our first angle is 10 degrees. And then we go all the way up to like 118 degrees. Okay, so we know the angles that these poles and zeros are going to make. Let's find the actual locations of these things. Okay, I'm going to come back here really quick. All right, so we have the angles that the poles make. We have the angles that the zeros make. Now, we need to find the actual Z1 and P1 values. Does your code automatically take format long? I think I just have that left over. Maybe I'll change it back, actually. The reason mine's printing so many numbers is because I had format long. All right. Okay. So let's determine the controller. Is the long format preferable? I think it depends on the application. I would say most of the time the short format is fine because you don't need like, you know, like 10 decimal points or whatever long gives you. I think I was doing something earlier that I was like, oh, I'm going to check a bunch of decimal points, and that's probably why I turned it on. Okay, what we're going to do is we're going to make a loop because we have many controllers to make. Well, actually only 10. So we're going to go from 1 to the number of controllers. Okay, so the first thing we're going to do is we're going to calculate the location of the 0 that corresponds to each angle. Now I'm going to put in a formula here that we derived yesterday. It's this one, tucked away in the corner. The location of the 0 is the real part of z star minus the imaginary part of z star divided by the angle that the the tangent of the angle that the 0 needs to make. So this is going to give us, this is the line of code that we're going to put in for that. Let's do it. So the real part of z star minus the imaginary part of z star divided by the tangent of the angle that z1 is making. And we have to make sure we put the index here because the index for my for loop is in, and it's going to go from 1 to 2 to 3 all the way up to 10. So I have to make sure that I change this. So this will give me the 0 for each of the controllers. Calculating location of 0. I bet you know what comes next. Location of pole. Fortunately, the pole has like the very same formula. So I could have just copied and pasted, but I didn't. And instead I typed all of that out when I could have just replaced this one variable, p, because we need the angle of the pole instead of the 0. That's impressive. You could call it that. Okay, now here's this is your favorite part, especially if you've named the code for today Donk. because we're going to calculate the controller without the gain parameter k, which is d with no k. That's what I've been calling it. No k. Or you can call it donk. So this is going to be a transfer function. And cool, you can make arrays of transfer functions in MATLAB. So each of these, this is going to be a vector of transfer functions. So what is this transfer function? Well, it's going to have the numerator, the denominator, the sampling period, which is important for discrete time systems. So we're going to have z minus z1n. So this is our numerator. We have our 0. And then we're going to have z minus our pole. So as we go through this loop, it's going to make 10 different possible transfer functions for our controller. But this, so far, it's without the gain parameter that we need. Let's go back here really quick. So this part right here is what I'm calling d no k. And to get d, we need this. Moshama says, hi, I just joined the channel. Do you happen to have an agenda of topics that you will review over the next few weeks? Well, right now we're doing root locus method, and then in the coming weeks, we're going to move on to state feedback. Either towards the end of this week or next week. Okay. The way to get k is you have to use the magnitude criterion. So the angle criterion is the first component. Now we have to use the magnitude criterion, which says, let's go down here. Magnitude criterion says this, that if you take your plant and you multiply it by your controller, hey, thank you very much. If we take the magnitude of this, it better be equal to 1. So this means that g evaluated at d star times k times d no k evaluated at z star is going to be 1. And so this is the way we solve for k. It's going to be 1 divided by g of z star times d no k z star magnitude of that. So this is how we solve for the gain. And this is the next formula we're going to throw into our code. And then we'll be done with getting the controllers. And then we'll just have to compare their relative performance. Okay. So using magnitude criterion to get the gain, k. We need the gain. So k, well, the nth iteration of this, whatever controller that is, it's going to be g, our plant, times donk, our nth controller. But we have to evaluate these at z star. We have to take the magnitude of that. And then we have to do 1 divided by that magnitude. Boom. That's the gain. And then, now that we have the gain, we can put together the controller. So D is the gain times the portion of D without the gain. And just like this, boom, we're going to make 10 different controllers. Why don't we run this code? Let's see if any errors have come up at this point. It's possible. There's a lot of semicolons and commas flying around, a lot of indices. I'm going to run it. I didn't get any errors, did you? Let's look at D1. This is our first controller. This is our second. This is our third. So you see the parameters are changing slightly. The location of the pole is changing. The location, like we have a gain in here. What are all of our gains? K1 is 58. What about the 10th one? Oh, I didn't change it to 10. Now it goes down to 2. Okay, so you can see we've made a bunch of different controllers. But the question is, which one do we want? How do I compare the relative performance of all of these? Let's go back here. What I want to do, the first thing to do to check the performance is calculate the closed loop poles. Because this is what really counts. Remember, the goal of the controller was to move our closed loop poles to the location Z star. But our controller will do that. But it's also going to generate a third closed loop pole that we have to keep track of. Will you post this code? I won't post this. I won't do it. You get slightly different numbers for K1 and K10. Is it all right if I send it in the chat? I just... for your K10, you got 12. Well, don't worry. You can always come back to this. I think you can... Like, my thing is... I mean, yeah, you can post it in the chat. That's fine with me. I just won't post the whole code because I really want people to go through this themselves and debug it, as you know. Okay, so what we're going to do, we're going to make the closed loop transfer function. And for each of these, and we're going to find out what the closed loop poles are. Okay, so the easiest way to make the closed loop transfer function in MATLAB is to use the feedback command. Good. And this takes two arguments. The first argument is the open loop transfer function. So the open loop transfer function is G times your controller. So just G times D is the open loop transfer function. Oh, character limit. Brutal. And then you also need to put a 1. Because this just lets them know that there's no extra transfer function in the feedback loop. Okay. And then we're going to calculate the poles of this. So let's make a variable like closed loop poles. And there's going to be 3 poles for each controller. So what I'm going to do is I'm going to use this colon. And what this colon means is each time I call this function, it's going to give me a column, which is the 3 poles. And it's going to place it in the nth column. So we're going to build this matrix column by column, filling it with poles. So we're going to use the pole command. So you can calculate the poles of a transfer function using the pole command. And which transfer function are we doing? We're doing the nth closed loop transfer function. Indexing as columns rather than rows. Filthy. I know. I guess you could do it a different way. This is just the way I want to do it. Okay, how about we run this? Let's run this again. I know some of you might have an error somewhere. Let's run it though. Wait, let's look at like our closed loop transfer function for the first one. You see it's third order. That's why there's going to be 3 closed loop poles. So let's look at closed loop poles for this transfer function. So this was our first one. So this is how you can access the poles for each. Boom. So look. We have 2 poles located at Z star. Because remember, Z star, these are our desired poles. And look, 2 of them, the complex conjugate where we want them. But we have this third pole, and this is bad. Tell me why this is bad. Negative real axis is number 1, but there's something going on here that's even worse. It's an unstable pole. Yes, the magnitude of this group, of this root, is greater than 1, and this controller that we made is unstable. Yeah, I can't believe it. This is why you have to be so careful when you use the root locus method, because it'll give you the 2 roots you wanted, but it's also going to give you a third root, and you got to keep track of it, and that's why we're making this code. Hey, how about we look at some of our other roots? Let's look at the second controller. What would you say about this controller? Better? Worse? What can we say about it? Very nice. Pretty good, not the best. Less bad, much better. It's stable. Yes. The big thing at least is it's stable. Some problem is it's on the negative real axis. Meaning that this root by itself contributes some like sawtooth dynamics. Meaning its oscillation frequency, it's going to oscillate every other sample. So it's going to make this jagged response. But it's getting better. Okay, we'll look at the third. Depends on what's dominant. Plammer, very good, very good. What do you guys think about this one? Muy bueno. This one looks pretty good to me. This is the best so far because it's on the positive real axis, meaning it's the dynamics of this pole are just purely smooth and exponential. This root is closer to the origin than these roots, which means it doesn't dominate these roots. What does it mean to dominate? We say a root dominates another root if it's slower. So this root, because it's closer to the origin, it's faster than these roots, and it's not going to bottleneck our response time. Okay, so this one's pretty good. Okay. Let me tell you what I want to do next. I think a good way to visualize these, you can, if it doesn't dominate, does that mean it has a trivial effect on the dynamics? Generally. If it doesn't dominate the roots, I would still look at the response, but it should have a trivial effect. Let's check out these responses, because this is something that I want to show you. I want to show you the Step response. How to do it in MATLAB for a discrete time system. And it's pretty easy if you have the transfer function. The reason we're going to do this, helpful for comparing controllers. Like we can look at the closed loop polls and we already have a pretty good idea of which controller is going to be best. Step response, best response. Okay, we're going to use the step command. Okay, and I want to use so the way the step command works, there's a couple ways to do it, but this is the way I want to do it. Let's start with let's start with our first controller, which we know is not good. Actually, let's do the second one. And I'm going to give it a time vector. So this will return the step response at the times that I specify. So I need to make this time vector. Let's do this really quick. So the settling time of our system, the way we've designed it, it should be around 2 seconds. So what I'm going to do is I'm going to make a time vector that starts at 0 in time steps of t, which is our sampling period, so that makes sense. And then I want to go up to like 2 times our settling time. Because if our third route turns out to be slower than the other routes, we might actually exceed this intended settling time for the controller. So I think if I do this, we're going to get the step of the closed loop transfer. Now, what this means for the closed loop transfer function, getting the step responses, that means we're providing a step reference, a unit step reference, meaning we want our output to go to 1. And so we'll see if we can follow it. Okay, so we'll make a figure. Plot t, y. And I'm just going to make some dots wherever it goes. And I'm going to make the marker size 16 just to make them like some pronounced dots. Let's make an X label, time, Y label. We didn't talk about what this transfer function physically represents, so I don't really have a physical quantity to put here. But I'll just call it response. Let's see if it works. I think this will work. So this is the second possible closed loop transfer function, which has a root on the negative real axis, but I don't think that negative root dominates our Z star roots. Ooh. Not so bad. Not so bad here. Wait, let's check something really quick so that you have some reference for what you're looking at. Like, what were our performance characteristics? We wanted an overshoot of 16%. We wanted a settling time of 2 seconds. And we want the steady state error to be 0. So does it do it? The overshoot is... What do we say about the overshoot? Is it just right? Overshoot is too large. Look at that. It goes up to like 1.2, 1.3 maybe. Overshoot's too big. I think that is a result of our third closed loop poll on the negative real axis, which is... What about the settling time? Settling time's good. It's like 2 seconds. So it's really that overshoot. Steady state error, spot on. It goes to 1. Okay, let's try our first controller, actually. I don't know what's going to happen here when it does a step of an unstable system. Wait, let's put in the reference here, like a red line of where we want to go, just for reference here. I'm scared to find out what happened. Me too. So I need to do a vector of 1s, and it needs to be the size of my time vector. So this is just going to plot 1. Let's go. Let's run it. I think I can just do this. It should be unstable. Why is it just... Oh, no. Do you see that magnitude here? 10 to the 6? It exploded, like, immediately. Okay. So not good. Not good. Okay, let's try our third controller. This one we thought was on the money. Or at least the best one we found yet. Wait, this looks good, but the overshoot... Actually, you know what? I think this overshoot might be due to something else. This does bring us to something important. Let's go back here. Let me show you the closed loop transfer function for that one. So we're getting the step response of this. Yeah, I know the plot thickens. And like just according to the polls here, like what are our polls? Closed loop polls. Polls, it's our third set. Let's look at them. So just if you look at these polls, our overshoot should be money. Can you scroll up to donk for a moment? Did you get the donk? So let me tell you what I'm thinking. We have zeros in this transfer function. Okay. When we calculated the formula for overshoot. Oh yeah, make sure you run a clear all. When we calculated the formula for overshoot, we made that formula assuming that we had a second order system with no zeros. It looked something like this. Actually, we did it in continuous time, but this is what our transfer function looks like. We used this to get our overshoot formula. When you use this for higher order systems like we now have, or if you use it for a system with zeros, zeros can affect your overshoot. Let's look at our zeros. If there's a poll command, I think there should be a zero command, right? I'm not totally sure, actually. I don't know if I've used the zero. Okay. So these are the roots of the numerator of the transfer function. I have to look more into this, but I think that having a zero on the negative real axis can increase your overshoot. So when you run into this kind of situation, and this is, could you scroll up to D with the K? Oh, you got it. Did you put a T here? You have to make sure D no K has this T for all your transfer functions. So this is what I was going to say. We use some approximate formulas to figure out what we think our desired closed loop pole should be. Now, what you're going to find in simulation or when you run your controller on hardware is maybe you have too much overshoot like we do now. What you want to do in that case is adjust your original Z star a little bit. So we know that if I were to decrease the damping or increase the damping ratio a little bit, the overshoot should go down. So what I could do is I could start like working with the Z star a little bit and recalculate this with a slightly larger damping ratio and see what happens. Okay, how about we try some other controllers though, because we had like 10 of them. I'm going to try this one. Let's try the fourth. Let's see if the overshoot just goes down. Wait, let's look at the roots first. So like aim for 10% overshoot to get 12% in the end. Amin, I think that's what I'm saying. Sometimes that'll happen to you. What I would do is first design it like this, but then just know that you might have to slightly change things. Okay, so what is this? Wait, what's the difference between the third and the fourth? Okay, the fourth has a real root that's just slightly larger. Let's try the fourth. I'm curious. Did the overshoot change? So this one on the right is the fourth controller. I think the overshoot went down a little bit. Six has a nice overshoot, but it's slower. Let's look at it. Oh. Okay, let's look at what's going on with controller 6. Let's look at closed loop poles for our 6th controller. Okay, this case, our third root dominates. The third root dominates our other closed loop poles. That's why the response is slower. And the response, the more dominant a root is, the more the response starts to look like the dominant root. So you see like, this is starting to look less like a second order response, and it's starting to look like just a first order exponential, just with a little wiggle on it. So it's starting to look more like the dominant root. Wait, how about we let's try the 5th. Or wait, which one did I do? Let's do the 5th. Isn't that going to be a little bit better? Oh, Did you see this one? 5 is good. The overshoot. Dude, the overshoot is 16%. Let's look at the polls. That was the 5th one, right? Okay, so wait. Does this root dominate? I'm not sure, because look at the way to check. Let's see how far those roots are from the origin. Look at this. The magnitude of our Z star roots are 0.67. Okay? That's how far away they are from the origin. This third root is slightly closer to the origin than these ones, so it doesn't dominate. So notice the response, like it looks beautiful. I like this one. Okay, people are talking about 7. What's up with 7? But so far, like, this is the one that I would pick. Like, the 5th controller looks amazing. What's 7? Ooh, okay, this is bad. This is bad because this route is very slow. This route's very slow. I'm guessing it's like, it's going to take a long time to settle. Like, what I'm going to do is I'm going to pump up the simulation time. Like, let's go to like 10 times the settling time. And we're going to simulate the 7th. Like, this one's going to be slow. Look at that. It looks like an exponential response that just has a little blip on it. And this is what I mean that you start to look like the dominant route. So this controller's bad because that 3rd route heavily dominates. 8 looks like it tried and then just gives up. Wait, so what is the... Let's look at the polls for 8. What are they? Oh, this should be unstable. This is going to go unstable. If we do this, the magnitude's going to go out of control. Wait, let's simulate just up to 1 time. Or actually, let's do like half the settling time. Because it's gonna get out of control. So we don't even have to simulate this very long. Oh, wait. What is this? What's going on here? Let's go longer? What is going on with that? What the? Oh! Oops. I think since it's pretty close to marginally stable, the divergence starts off a bit slow. Yes. And note, this is, because this is on the real axis, it's not going to oscillate. Like the first unstable system we had, it was a negative real root that was unstable. And a negative real unstable root is going to like oscillate like crazy. This one is just going to keep peeling off in the same direction. Look at yeah. Whoever said it just wanted to give up. It started, then it's like, nah, man. No thanks. I added to my code an if statement that excludes system with negative poles and poles greater than 1. Could this cause problems? No. So what I wanted to give you guys with this code is give you like a starting point. There are lots of cool modifications you can make to this code. Like what I would do, you know that you want to rule out unstable systems. Okay, good. Something that we haven't added to this that we could. You could see how this responds to a ramp reference. Actually, maybe we'll do that Wednesday. But you can calculate the KV value. KV tells you how close you can follow a ramp reference. Hey, Stony, new follower from Barcelona. Hey, welcome. Thanks for joining. We're doing control systems. Okay, guys, This is the beautiful one I would pick. Would it be a good strategy to pick a controller whose 3rd root is close to the magnitude of the 2 roots? Jim Alino, I like that strategy. Was that a Spanish accent, Dr. E? And it was a Spain Spanish accent. Oh, Pika has a question. Was anybody able to see where they got points off on the midterm? I was able to see I got points off, but not exactly where I went wrong. Just points per question. I told the graders to leave a comment. So if they didn't, I'm going to have them go back and leave a comment. What I'm also going to do is I'm going to post the solution so you can do like your own audit, okay? I'll post it on Box. So you can go look at your problem and take a look for yourself. But I'm going to have... There's no comments? Okay. I'm going to have them go back and add comments. I told them to do that. I'm surprised that you didn't have comments. Okay. Will the project be posted today? Ooh. It should be very close to... I think it's going to go up today. This code will help you with Project 1. Project 1 is designing a controller for the motor. Oh no. Wait, did you just see what happened? It's designing a controller for one of these DC motors on here. Carl says, take your time. No rush. Wally lost a wheel. No, Project 1 is fun because we'll get to compare how your controllers perform. This code is a very good starting point for that. No, I think it's totally manageable. Are we going to keep editing the code on Wednesday then? I think so. I think we're going to come back and see how this responds to a ramp input. Maybe add some more features. But this is the good baseline. This is a code that you can keep using as you design control systems for whatever. Can you do a semi-slow scroll through the code? Because I have an error. Sure. This is the top. The tippy top right here. We're doing the slow scroll. Hey, have a good one, Belkit. Error using dynamic system poll, line 37. Input to roots must not contain not a number or infinity. Wait, can you zoom out a little? Hey, have a good day, Primordial. Wait, let me finish my slow scroll. Gotta stay focused. Almost there. Yeah, that's it. The only thing I have to zoom out for is this line up here. So the only thing you gotta see is this. Actually, you know what I can do? I can make a dot, dot, dot. Boom. Actually, that doesn't help that much. What if I do this? Dot, 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 boom. You can do that. So now it all fits. Let's go back over here. For the last homework problem, do we need to check for the third root? No. That's okay. Only whatever I asked for in that one. Hey, enjoy the day, Benny. Always a pleasure hanging with you guys. Hey, you have a great too, Amin. Everybody, we're going to call it here for today. Hope you enjoyed. Hey, that guy who stinks, see you. Is MATLAB for Homework 4 optional? Yeah. It certainly is. Homework 4, you just do it however you want. In fact, the graphical method is perfect for that. That's kind of what I intended. All right. Enjoy your day. Adios.